Okay, so today our goal is to get far enough that I can give you some problems and stuff to work on and start kind of solidifying these concepts. Um, and so I'm going to first uh, give you kind of the most basic roadmap of the laws of physics that we're going to use. So um, these are the laws of physics for the semester. Um, the first one is conservation of energy. That's going to be the one we come back to the most often during the semester. And we'll talk about this as the first law of thermodynamics. So that's just another name for it. Second, we'll talk about conservation of mass. Um, and we'll often refer to this as the mass balance equation. And then third, the total entropy can never decrease. Once you've produced entropy, you can never make it go away in the universe. You can hide it somewhere else in the universe, but you can't make it go away. So total entropy can never decrease. Um, and this is the second law of thermodynamics. And all of these we're going to do with two different types of analysis. The first is going to be called a closed system. This is really the one that you're used to. Because you've mostly done calculations where you're dealing with solids. I mean, the people who've taken physics one, that's what you tend to focus on is solids. And a closed system is one where over time you track the same material. So at instant one, you're tracking a ball. At instant two, you're still tracking the same ball. It's just somewhere else with different, properties or whatever. So a closed system is one where over time you track the same material. There's a different type of analysis that's often useful for fluids. And by fluids, I mean liquids and gases. Those are both fluids. And that is a control volume analysis. Um, so in a control volume analysis, over time, you're tracking the same space, but different material is flowing through it all the time. Um, so let's say that material flows in and out of this space. you can probably imagine why an analysis like that, if you can figure out how to do it mathematically, would be useful for a liquid or a gas. You don't want to have to try to track every single molecule that you had contained here. 10 seconds from now, some's going to be way over there, some's going to be way over there. It'd be a lot nicer if you could just track a space and take into account that some of the material is leaving and some of the material is coming in, you know. And so this is sort of the basics of the analysis that we're going to do this semester. Um, and pretty much always we're going to start with a closed system because it's simpler mathematically. So we'll do the first law with closed systems, and then later on we'll go to the first law for control volume analysis. I want to say a little bit about the first law right now. So the first law of thermodynamics, I'll come back to it again in a week or something, and we'll get into it in detail. But this is going to be the most important equation in this class. And so the first law of thermodynamics looks like this, and this is for a closed system. Closed system. And it looks like this. The change in energy of the system that you're focusing on is equal to Q minus W. And the sign convention here is very important. And it's going to be the same sign convention we use over the whole semester, and it can be very confusing. And so I want to start emphasizing that now. So really all this is saying, the first law of thermodynamics, conservation of energy, is saying something very simple. It's saying that the change in energy of your system is equal to the amount of energy that's exchanged due to thermal sources, due to temperature changes, plus the amount of energy that's changed due to the application of forces, the work. Okay? That negative sign kind of obscures the simplicity of it, but that has to do with the sign convention we're going to use. So U is the heat added to the system. And the meaning of heat is a change in energy due to a temperature difference. Okay, so in everyday speech, when you talk about heat, you might sometimes think of it as kind of temperature, something like that. But we're going to talk about it in a very specific way, and it's not temperature, it's an energy change, okay? It's a difference in energy between 2 points in time. And that heat Q is only going to be positive if energy is added to the system through heat, okay? Now, what about the work? What about that negative sign? The capital W is the work done to the surroundings by the system. And work is a change in energy due to the application of a force. Okay, so heat and work are both changes in energy, um, but one is due to temperature differences, one is due to forces. And Q is going to be positive when heat adds energy to the system. W is going to be positive when work removes energy from the system. And that's why we have that negative there in the equation. It's a pain in the butt. It seems unnecessarily complicated. But there is I stand by that. It's unnecessarily complicated. But there is a way to kind of make sense out of why this is. Okay. So the big question is why? Why do we have this funky thing where heat is the heat Q that we're always going to use in calculations is energy added to the system, and the work W is energy removed from the system. The most important thing in thermodynamics, and the most important thing in thermodynamics as thermodynamics was being developed, or let's say the most important use of thermodynamics, is a power cycle. And so think of what happens in a power cycle. Okay, so a power cycle, first of all, what is that? That's the that's the thermodynamic cycle that you use to power a engine, like an old steam engine, a train. Uh, you put heat into the system and you got resulting work out of the system. Same thing with a power plant. You put energy into a working fluid with some kind of high temperature source, and the result is that work is done on the surroundings. Um, that can be work that's done on some kind of dynamo that produces electricity, or it can be work produced generally to power some kind of mill or to turn wheels or whatever. But the idea in all these cases of a power cycle is this. So imagine that this is your cylinder. Oh, my computer wants to rest for a second. Come on now. This is going to crash. So let's represent a power cycle as a cylinder and a piston. And a lot of times in this class, we're going to simplify general things into cylinders and pistons. So let's say that we have the gas here. Enclosed by the piston. And what we do is we raise the temperature of the gas through heat. So heat is coming in this way. And the result of the power cycle is that piston moves up and does work on the surroundings. So if you generally think about a power cycle, we get energy added to the gas through heat, and we have energy removed from the gas, the working fluid, through work. Okay, so you can always have this in the back of your mind as a way to remind yourself what the sign convention is for heat and work. Um, so heat here is added to the gas. So that's positive Q. And work is done by the gas, which is positive W. Okay, so that's why we have this sign convention. In a power cycle, both of these two things are positive. Okay, so the key thing to remember here the first law really says something simple. The change in energy in your system is equal to the energy added through heat, added to the system through heat, plus the energy added to the system through work. Okay, there's nothing surprising there. If you add energy, no matter how you add that energy, it increases the energy in your system. It gets obscured by the sign convention, but the sign convention says if you're calling something positive W, it actually means energy is being lost from the system. Okay, so let's think about an example of this. So let's say that a system has 400 joules of work done on it over a time interval. While giving off 600 joules of energy as heat. So first, what's the value of Q over this time interval, let's say? What's the value of W over this time interval? And finally, what's the change in the system's energy over this time interval? Okay, well, Q is positive if energy is being added to the system. Is energy being added to the system or removed from the system here? Removed. So for part A, everybody follow that, see that? So Q is equal to negative 600 joules. Okay. B, what's W? Well, W, remember, is positive if energy is being removed from the system or added to the surroundings through work. This is adding 400 joules of energy to the system. So is this positive or negative? Negative, yep. And so W is equal to negative 400 joules. And now we can put this into the first law of thermodynamics. So the change in energy is equal to negative 600 joules minus negative 400 joules, which gives us negative 200 joules is the change in energy. So the energy in the system has decreased 200 joules. Okay. Okay, so there are going to be a couple of questions sort of like this on the homework that I assigned tonight. But that's really all we're going to do with the first law for now. We'll come back pretty soon. The next thing I want to talk about is properties, states, and processes. So this is just kind of defining some terms. A property is a single measurement that represents a system at an instant. So a property can be temperature, pressure, volume. Later on, it can include entropy, enthalpy. So these things are all single measurements that represent a system at an instant. And that's definitely not all of them, but that's a bunch of them. A state is also at a single instant, but a state is all of the properties representing a system at a single instant. So you could measure the temperature in this room. You could measure the pressure in this room. Those are all properties. But this room is defined by all of the measurements that you could imagine taking. Okay, this room just has one state at this instant. And so we'll talk about the property, the temperature property at this state versus the temperature property at that state or whatever. A process is a little different. A process doesn't deal with a single instant. It deals with the transition between two states. And one thing I want you to notice here is that conservation laws um, an example of a conservation law is the first law of thermodynamics. Um, always deal with processes. So you never use conservation of energy to just analyze a single instant. You always use it to say, here's some stuff happening when this skateboard is at the top of the hill. Here's some stuff happening when the skateboard's at the bottom of the hill. And we'll use both of those together to figure out, what changed. So conservation laws always deal with processes. Okay, so let me illustrate these in an example. So let's say that we have a gas that has an initial pressure of 2.0 times 10 to the fifth pascals. Um, that's the same, by the way, I'm going to use that notation a lot, but that's the same as 2.0 times 10 to the fifth pascals. Um, this is just kind of the way you enter it into a calculator, so it's a little shorthand kind of. Be sure you don't write this as 2.0 times e to the fifth power. That's a totally different number. So, yeah. So it has this initial pressure. It has an initial temperature of 350 Kelvin. And a volume of 0.6 cubic meters. It's then compressed to a pressure of 3.0 times 10 to the fifth pascals, a temperature of 400 Kelvin, and a volume of 0.3 cubic meters. Um, what are the properties the states and the processes? Um, okay, well, there are two different instants, and so there are two different states. So I'm going to do it like this. State 1 has the properties 2.0 times 10 to the fifth pascals, 350 Kelvin, 0.6 cubic meters. So these are properties State 2 um, has the properties 3.0 times 10 to the fifth, 400 Kelvin, and 0.3 cubic meters. And these three things are all properties. And the process, let me write it as going from state 1 to state 2 is the only process here. Okay. The state thing, I mean, I think that kind of makes sense with the way you think about state as a word in English language. Like if somebody's like, what's your state of mind right now? And you think about all the things going on, like I crashed my car, but I did just have some ice cream, so like it's complicated. Each one of those thoughts is a property, and all of those thoughts together make up your state of mind. There are two types of properties. And they're called extensive and intensive. Um, Laws of physics usually deal with these extensive properties. But intensive properties are going to be important to us because we'll be able to look them up. And we'll talk more about that in a couple weeks. So this is more common for us because we can look these up. And you've all taken chemistry 1. Like an example of these intensive properties is like the ideal gas law. Well, so if you have a gas that can be represented as an ideal gas, um, and say, pressure and volume, that's enough for you to figure out what the temperature is from the ideal gas law. Okay. There are similar relationships that we can use to relate internal properties. The ideal gas law is only one of them, but we're going to use website calculators and stuff to be able to look up these intensive quantities. But eventually, we're going to have to relate these intensive quantities to extensive quantities because those are the ones that show up in the laws of physics. Okay, so let me define what an extensive property is. Um, Extensive properties are only defined uh, if you choose an amount of material. Okay, so like for example, let's think about temperature. In measuring the temperature of a room, is it important to know how big the room is? No, you can put the thermometer anywhere and take that measurement. So we know that temperature is not going to be an extensive property. Another thing required for extensive properties is if you partition a material into pieces. So let's say, so we have, this is our material. And let's say we split it up into these 4 pieces. And let's, call this region 1, region 2, region 3, and region 4. If P is an extensive property in each of those regions, then this has to be true. The total P for the whole thing has to be equal to the sum of those individual P's. Okay, so thinking about it this way, let's think about a few different properties. So again, let's start with temperature. If this is the room and we split it into 4 pieces, and we take the temperature in each one of those 4 pieces of the room, say that we get 70 degrees over here, 70 here, 70 here, 70 here. Does it make sense that the temperature of the whole room is 280 degrees? No, that would be a catastrophe. So temperature is not extensive. But let's think about volume. Okay, so if that has whatever it is, 5 cubic meters, and that is 5, and that is 5, and that is 5, does it make sense that the volume of the whole room is 20 cubic meters? Yeah, that makes sense. So some examples of extensive properties. Our volume, and we'll denote that with a capital V. Mass, that makes sense. If you take a table that has a certain mass, split it up into 4 pieces, the masses of those individual pieces have to add up to the total mass. We'll denote this with a lowercase m. Internal energy, we'll denote that with a capital U. Entropy, we'll denote that with a capital S. And, these can go on and on. There's a whole bunch of these. Usually, extensive properties are going to be denoted by capital letters, but not always. You can see mass is an exception. Mass is we're going to represent with a lowercase m, but it's extensive. So usually these are represented by capital letters. And if you go back to the first law of thermodynamics that I wrote up here, um, all of these are extensive properties. Um, well, I guess these are not really properties, but they do depend on the amount of material you're looking at. Um, E, though, is the total energy in your system, and that is an extensive property, and that's why we're using a capital letter there. Okay, intensive properties. So let me say the most important exception here is M. That is an extensive property, but we're going to use a lowercase letter for it. Okay, now what about intensive properties? Well, anything that's not an extensive property is an intensive property. Um, and intensive properties are always measured per unit. And for us, it's most often going to be measured per mass, per unit mass. Um, so some examples of intensive properties. Our density, that's going to be represented by the Greek letter rho. Looks like it's sort of a scripty cursive P. Um, and this is defined as mass per unit volume. Specific volume, and we'll represent this with a lowercase v. A lot of times these intensive properties are going to be just the lowercase version of what the extensive version would be. So volume is capital V, specific volume is lowercase v, and that's equal to the volume per unit mass. I put these two next to each other because notice that these are just reciprocals of each other. And that means if you know one of them, you know the other one. Pressure, that'll be denoted with a lowercase p, and that is equal to force divided by area. Um, temperature uh, is a capital T. And in order to write out what temperature is measured, you know, how that's measured per unit, you'd have to get into the physical definition of temperature. I'll just leave it like this. We're going to just think of temperature as something you measure with a thermometer. Um, intensive properties usually use lowercase letters. The most important exception to that is temperature. One other thing about intensive properties. So the most important ones for us are going to be measured per unit mass. But they don't have to be. They can be measured per unit other stuff. Pressure is force per unit area. So one thing I want you to notice is intensive properties given with an overbar. I'll draw what I mean. Are measured per mole. Okay, so for example, if you see a lowercase v uh, with a line over it, an overbar, um, this is volume per mole or molar volume. We won't deal with that too much, but we'll see it sometimes. Okay, any questions about that? Yes.
Intensive properties typically derive from extensive properties, or is that
They all, yeah, you can always, always is a scary thing to say, but I think you can always, any intensive property comes from an extensive property. And then you sort of do it on a per unit basis. Yeah. I think that's right. Any other questions? So we did a lot of definitions and stuff like that today. I'm going to give you some questions to sort of go through to just help you solidify this stuff, stick it in your brain. Next time, we're going to start talking about pressure, and we'll start to be able to do some calculations. So next time, I guess we'll talk about pressure, and hopefully we'll be able to start talking about temperature also. Okay, that's all.